Hello everyone. Thank you very much for inviting me today to present my work. So today through this presentation we are going to talk about microarchitectural vulnerability assessment and mitigations. We are also going to look into different aspects of where security is headed and what can be a way forward to modern computing paradigms. So let's have a look on the outline of the presentation quickly. Today, we will talk about the information security perspective and the problem statement. Later on, I'm going to talk about my doctoral research about detection and mitigation framework for side channel vulnerabilities and microarchitectural vulnerabilities. We are also going to talk how to design inherently secure systems, which is more or less the part of my postdoctoral research. And toward the end, we will talk about the conclusions that what is the way forward for security and where we are headed in the future. So let's talk about the problem statement at large at first. So in modern era, security is a shared concern by many application domains. Either we talk about health, e-governance, banking sector, we name it. Every critical infrastructure requires security today. But behind this critical infrastructure, there lies a computing infrastructure that can make these services either secure or insecure. So let's have a look at that computing infrastructure that can make these services vulnerable. So here is an abstract view of conventional computing stack, which is very successful due to one reason, that it allows the evolution of software from hardware independently. However, from the security perspective, the problem with this model is that all the layers are leaking information. Either we talk about software, we talk about hardware layers, all the level and stages of the computing stack is leaking right now. So the question is, what the state of the art reports. An overwhelming amount of literature establishes that information leakage is possible even under the safe software because the underlying hardware is vulnerable. So in this context, the question is that what went wrong in the process? Before, security has always been a design consideration, even if it was not a primary consideration. Research points us to a recent discovery of side and covert channel information leakage as being the trigger point for the paradigm shift in computing from security perspective. So the problem of information leakage through this side and covert channel is broad enough to practically impact the entire computing stack. So let's have a look at how a software execution on the underlying hardware can be a problem. For instance, here at the functional unit, we are encrypting a piece of information to secure it using conventional security techniques. However, while doing so, a lot of side channel information is relayed, like power, timing, access pattern. So having this side channel information in the first place is not a problem. But using this side channel information to compromise the data we are trying to protect, as well as the encryption process itself, is the real problem. So this is basically the bigger threat, which is challenging the conventional security paradigm today, which needs to be changed, which needs to be overlooked. So to conclude on the problem statement, let me just elaborate an example where we have two processes. One is malicious and the second process is doing the encryption, as I just explained you. So if the process one wants to get to know the direct information of process two, the system software is not designed in such a way that it does allow it. However, both the processes are using shared hardware resources like last level cache, which allows the malicious process to get to know the side channel information of process two, like timing information, cache hits, cache misses, access patterns, to retrieve the sensitive information of the process two. So a simple side channel information like access pattern can reveal a lot about what is being computed, and that is the problem of today. So in this backdrop, Intel x86 architecture has proven to be the biggest casualty of security vulnerabilities, if not the only one. So let's have a look at an abstract representation of Intel's shared memory architecture. There is a computational part, you can see there is a storage part. In computational part, we have multiple logical CPUs share the same physical cores, and storage part where we have first and second level of cache, which are shared between CPUs that are related to the same core. The last level cache, which is inclusive memory architecture. So Intel x86 architecture has been leaking critical infrastructure both at the computational level and at the storage level, and I'm going to show you how. So if we talk about the storage perspective or caches in particular, it is the part where most of the side channel information leakage has happened on Intel x86 architecture. So this is due to the inherent design features such as the inclusivity, we name it, hierarchical organization of caches, static structures that allow multiple processes to share cache memory locations among them. So such well-defined static relation among multiple memory addresses enable the attacker to plan cache conflicts with other processes, which could be the victim processes. So, and such planned cache conflicts would allow a malicious process to extract information related to presence or absence of a particular address in cache through just simply measuring the timing difference like cache hits or cache misses. That's all. This makes the attacker to launch an attack. And if we look at the computational perspective, the performance optimization features, which were considered to be very nice for modern architectures, such as out-of-order execution, speculative execution in the contemporary architectures, even if the execution information is discarded, the secret information stays at cache level. And this is the vulnerability. A simple timing attack can reveal the victim's execution or the victim's information, and it tells a lot and called as side channel. So from the storage part, from the computational part to the network interconnects, all the part, we are right now under attack, and all the levels are leaking the information. So looking at the shared memory architecture, there is a long list of side channel and covert channel, which is a non-exhaustive list I am presenting here, have targeted both the computational part and the storage parts equally. So as you can see, there are many attacks targeting memories, physical cores, logical CPUs, and the list of this attack is very long. And this is not only Intel x86 which is under threat. The same problems are happening at ARM, at AMD. So we are the challenge of information security is getting very large, where we need to point out, where we need to see what is happening. So if we look at the state of the art on defenses for these attacks, there are solutions both at hardware level and software level, such as partitioning-based, randomization-based solutions in hardware, noise-based, scheduling-based solutions in the software. However, most of these defenses are specific to the vulnerabilities and specific to the attacks. So what is missing in these solutions is that they do not provide coverage for a large attack vector. They do not provide system-wide solution, and they are very heavy on performance. So in this backdrop, my work is based on the following facts. A complete attack surface is not known yet, and it is rather expanding from storage to computation and to network interconnects. New leakage channels are discovered and more sophisticated attacks are emerging every day, and they are going to keep on exposing the contemporary architectures. So even the intended secure architectures like Intel SGX, ARM Trust Zone are reported to leak information. So these recent developments have made a paradigm shift in security. At one hand, security is certainly becoming a first-class design constraint, and on the other hand, there is a prevailing consensus that the security must be ensured across the board, across all the levels of the computing stack. So there are possibly two ways to handle this problem. First is a secure by design solution, where we have bug-free software application, where we have operating system and hypervisor layer with complete isolation, where we should redesign a non-leaky hardware. But this solution seems to be a thing of future for now. An alternate approach would be to have systems that are secure at runtime, where attacks can happen, but their impact and their value can be contained here. So during my PhD work, I favored on working on secure at runtime. We remain in the contemporary architectures, the existing architectures, and we provide the solutions at runtime to detect and mitigate them. So in this context, my PhD work argues that in the absence of secure by design solutions, the system software must be empowered to provide need-based protection to the computing base. My contributions can be divided in 3 different modules. One is attack vector development and analysis, and then the 2 frameworks I proposed for it is runtime detection and runtime mitigation for cache side channel attacks. And now I'm going to, in future slides, I'm going to talk about each module one by one. So now let's talk about the two modules which I have proposed in my PhD detection and mitigation framework. Coming toward the first module, attack vector development and analysis, let's talk about it. So if we look at the victim's perspective, what is happening? Side channel attacks are actually changing or altering the footprint of the victim and where it is changing it in the cache. So it is altering the cache behavior. For example, how? In terms of access timings, in terms of cache access, in terms of access patterns, in terms of cache hits, cache misses. So total number of cycles, total time of execution. So this is the footprints which an attacker is monitoring to retrieve the information of victim. So such information can be very valuable for us if we somehow are able to monitor this. So here I present different hardware and software performance counters which alter not only the cache behaviors but also the performance optimization features as the system-wide counter which cover both the storage part and the computational part I was just discussing earlier for the transient execution attacks. So performance counters were taken as an indicator to know the behaviors when an attack is happening. So here we can see the execution traces of different performance counters under prime and probe attack, such as L1 data cache miss, L3 total cache accesses, L3 total cache misses, total cycles under no load conditions, where the best scenarios in papers and attacks describe that they are under no load conditions, which is actually not the realistic scenario. So all these representations show that the attack behavior in red holds a quite discernible behavior from no attack, which is in green representation. So these are the results generated when attacker and victim are the only load on the system. But it is quite noticeable here that performance counters are something good indicator for behavioral analysis of system under attack and under no attack. So I believe a simple threshold mechanism can really generate if you are somewhere here, if you go beyond this value, you are under attack. If you are below this, you are not under attack. But what happens? Let's talk about that. The second module, which is runtime detection and how we are going to take these behaviors for detecting it. So we saw that appropriate performance counters can reveal interesting information about the cache side channel attacks. Now let's have a look on the representation of the same counters when we are under load conditions, where we introduced memory and CPU intensive benchmarks and where we launched multiple attacks, as you can see in the list here, which are happening at the runtime. And this is the realistic scenario in which the world should be working. So you can see that the green behavior of no attack is no more discernible from the attacking behavior. So this is a complex situation where a threshold-based mechanism is just not able to determine whether we are under attack or under no attack. So therefore, to distinguish such complex behaviors, machine learning proved to be our friend to help in automatically learn and classifying the attack and no attack behavior. And this is the time when I propose that machine learning can be a useful indicator in security. So to do so, I have tested many classical machine learning models existing which train and do binary classification. And here is a list of those machine learning models. And I experimented 12 models and selected those which are higher in detection accuracy, which are lower in implementation complexity, and offer a moderate performance overhead, because we don't want to lose the hard-earned performance benefits which the architectures have achieved in last 20 to 30 years. So just to sum up the single attack detection, I have given a big picture that how it works. So it sums up basically the detection module. It comprises of two main modules. The first module is about attack vector analysis, where we leverage the runtime behavioral analysis of a microarchitecture from hardware and software performance counters. Then we have some selected machine learning models. This behavioral analysis is then passed to machine learning models, where we train them for this activity. And at runtime, we are able to detect the attack or no attack behavior. So this is just one model on which I have started or initiated to work on. Then we also worked in single versus multiple models detection, and we also went to ensemble, where we have a voting based mechanism for different type of 9 to 10 to 12 attacks attacking the system together, and the voting mechanism detects the attack by learning these behaviors. So now let's have a look on the use case attacks, which I have used for cache side channel attacks, because these behavioral analysis or detection has to be performed on some real-time attacks. So I have reproduced a library of 9 use case attacks, which are cache-based attacks or the transient execution attacks with different crypto systems or no crypto system at all, because I believe the problem is not with the crypto. Problem is on execution of software on the hardware, and then with different OpenSSL versions and different variants of the attacks with full key, half key recovery, full message exploitation. So we have developed a repository to test these attacks. So just to showcase you one result of the detection of flush and reload attack on RSA crypto system, we can see that all the machine learning models performed with a nice detection accuracy in medium load, zero load, or in high load conditions with a speed which is very minimal. And we can see that QDA really performs well by giving us 99.5% of detection accuracy in medium load and 0.9% speed of the detection at the finer granularity. Just to mention that we tried different granularity scores to finer, and we were able to detect the attack before the 10 bits of 1024 bits of RSA crypto system was computed, and then there was a negligible misclassification on the results on false positives and false negatives, and the overall overhead of the system was negligible, like 0.6%. So here we can see that results are showing that detection using performance counters and machine learning can be a helpful direction. Now let's see if this mechanism or methodology was able to look the same on the computational attacks or with different models, what needs to be changed if the proposed mechanism work effectively for attacks which are not crypto based, which are computational attacks. So maybe many of you have heard about it. In the year 2018, there was a big breakthrough and multiple security breaches in modern computing architectures. International media covered it all over the world. There were researchers who reported these security breaches named as Spectre and Meltdown. So in the following part, I'm going to quickly illustrate you what were these vulnerabilities and what was exploited actually in these attacks and why they are so popular. So in 2018 and onwards, 2 recent vulnerabilities and their multiple variants are discovered till 2021. So both the vulnerabilities exploit the performance enhancement features of current computing systems. Both the vulnerabilities depend on 2 phases. The first, for example, in Meltdown, it takes the benefit of out-of-order execution, and in the second phase, it performs a cache side channel attack, a simple flush and reload attack, to launch the attack and to know the victim's secret. And then Spectre also is 2-phased, uses branch prediction, and in the second phase uses a cache side channel attack to mount an attack. So here I would like to just show you quickly one result out of many on the meltdown detection, where we have used different hardware performance counters, software performance counters. The scope of events is not only cache based because it is using performance events, it is using optimization features, and it is using cache events too. So we have used system-wide events, we have used cache events to detect the attack at both its levels, first level and the second level. So this figure illustrates 2 system-wide performance counters. One is showing the total number of instructions per process, other is showing the corresponding page faults generated by each process. So figure on the left illustrates the total number of instructions per process for 4 different processes, 2 benchmark, 1 web browser application, and 1 meltdown attack. So as illustrated, the meltdown process demonstrates much less number of total instructions, as you can see executed on the left. So whereas the corresponding page faults generated by the same process are much higher as compared to others. This was very abnormal to observe. So similarly, the processes having a larger number of instructions demonstrate nominal amount of page faults. And why this process is giving a lot of page faults with very less total number of instructions. So this result illustrates that the meltdown process exhibits a disproportionate quantity of page faults, which is abnormal. And just to elaborate quickly, one result that we tried different machine learning models on this, LDA performs really well. In average load, we were able to detect the attack at 99.91% accuracy at the speed of 10 microseconds, which was the finer granularity, and with negligible false positives and no false negatives. And the overall detection overhead was 1.91% overall. So this was about the computational attacks. So we came to know we are able to detect the attacks at storage part, at computational part, and detection using performance counters and machine learning can be some helpful direction. Now let's talk about the runtime mitigation. What happens when we are detected? So this is a big picture of all the PhD work where we have attack vector analysis. We do the behavioral analysis using hardware software performance counters. This behavioral analysis is then passed to the user space where my second module, the runtime detection, is working, takes machine learning into account, does the behavioral analysis, tells us either we are under attack or not. If we are under attack, this information is passed to the kernel space where my third module, runtime mitigation, is working. So this module basically evaluates all the vulnerable processes currently running in the system and separates trusted processes from the untrusted ones. So finally, it resumes the execution of trusted processes while takes an appropriate mitigation decision for the untrusted processes. So just to showcase you one result here on the effectiveness of detection-based mitigation of flush and reload attack on RSA crypto system, you can see this figure is a timing-based efficiency where the blue bars depict the RSA crypto system running alone, RSA crypto system running with flush and reload attack, and its timing is too much because of the continuous flushing and reloading of the attacker due to its activity. And the green bars here represent you the efficiency of my proposed mechanism. Just to summarize here that we were able to detect and subsequently mitigate the attack in less than 2% of the attack completion. And this part of my work and methodology was highly appreciated by Secure IC, and they have used this methodology in one of their project, Horizon 2020 project named as Team Play. They were part of my jury also. They appreciated this methodology a lot. So I'm happy to show this encouraging result to you. And now let's talk about my postdoctoral activities, where I left the runtime solutions. And here let's talk about how secure by design systems should look like, which is actually the part of my postdoctoral research, that now we should move toward the solutions where systems are more deterministic and more transparent, and we start to design systems for security reasons where we don't occur to have these attacks. So from this slide, let's discuss the research key challenges we are dealing nowadays. So if you look at the prevailing attack surface, which is very interesting, that in this illustration, that the challenge of information security is enormous. There is a continuous race condition happening between the attackers and the designers. For instance, the information retrieval attacks have a great and wider attack surface. Attacks are at software level, attacks are at hardware level, attacks are internal, attacks are external. If we look at the classification of the information retrieval attacks, it is just state of the art. Like the classification tells that the attacks are software on software and then software on hardware too, and same for the hardware, hardware on hardware and hardware on software attacks. They are targeting the protected software and the protecting environment, even called as trusted computing base. So as you can see that the attack surface is so widespread, the challenge of information security is quite huge and tremendous. The only thing I can see here is that security is a system-wide concern, and software alone or hardware alone cannot provide sustainable security. So let's have a look that what can be a way forward to deal with this research challenge. So I'm proposing to design an inherently secure computing system. I have carefully highlighted 3 key challenges, and if I'm able to achieve these 3 key challenges, this will be a roadmap to take me to secure by design computing. So the first key challenge would focus on attack surface and vulnerability assessment. This key challenge will provide proper tooling and models to assess the scale at which the systems are exposed today, because till today we just don't know how much vulnerable we are So, and the second key challenge will focus on the system software, specifically on the design of secure operating system and hypervisor. This key challenge will strengthen me at the system software against the attack surface we just discussed. And the key challenge 3 will focus on securing the architecture in order to prevent hardware vulnerabilities in the attack surface I just explained. So now let's have a look on the methodology around these key challenges. So let's talk about my first key challenge, which is about attack surface assessment. So attack surface is unknown till now, till 2021, due to lack of transparency. Security from obscurity must come to an end. There are attacks which are reported at the microarchitecture level and all the above layers till today, till to date. So I propose to better understand the microarchitectural components which are undocumented till today. So for security reasons, how these microarchitectural components behave, like hardware prefetchers, branch predictors, CPU caches, we just don't know. So we need to understand these microarchitectural components first to learn their behaviors and to develop tools and techniques for automated vulnerability assessment. So I propose in this illustration to develop these traces of microarchitectural components by using, before in my PhD, I have used indicator for performance counters. Now I propose to also work on hardware emulation platforms who can develop these traces. And from these behavioral analysis of traces, we can develop tools and techniques and models using machine learning to do automated vulnerability assessment. Okay, so in this key challenge, I propose to assess the level at which we are vulnerable today, but I do not propose to change or modify any of the layer at this phase. Now, in my postdoctoral activities, as this key challenge is one integral part of my work or my project, so I have started to work in NR ArchiSec project there, and we have done traces of the memory subsystem and used by Gem5 and used different deep learning models for vulnerability assessment and classification, and for rowhammer vulnerabilities. The results seem to be very promising, and we have recently published a workshop paper in CodaSpy. And there are some other works which I have published on the same topic. Then for key challenge 2, it will focus on secure OS and hypervisor, mainly because there are two most privileged layers in the computing stack, the operating system and hypervisor. Existing vulnerabilities show that the attacker can exploit certain permission checks applied by these layers, as you can see here. So the operating system allows different user applications to be scheduled on cores, memory, network interconnects, and execute. So operating system must be empowered enough to delete or to finish the residual microarchitectural states by the operating system, which are left, as the arrows show, after the program execution. So for that, I have proposed multiple enhancements like serialization of processes, restrictive speculation, cleaning the cache states, introduction of even new horizontal privilege levels to the computing stack. So in this key challenge, I propose to redesign the operating system and hypervisor for security. And for this key challenge, I have worked on mitigations proposed as the OS-based attacks like Spectre and Meltdown. And this paper has recently been accepted in a European Test Symposium. And there are some other works which we are doing on hypervisor-based attacks, and we are trying to mitigate these attacks at hypervisor layer. Now my key challenge 3, which is a long-term key challenge, I propose to work on securing the architecture from different aspects like microarchitecture level and instruction set architecture. I propose to do the systematic revision and extension of instruction set architecture, because right now it takes into account the architectural states, as you can see in the green, but it does not account for the extra architectural states which should be a part of the instruction set architecture to cope up with the challenge of many attacks like Spec, Meltdown, and many more coming nowadays. So I propose to do systematic revision and extension of instruction set architecture to remove these unknown microarchitectural states. So these are the three key challenges on which I am working, or I intend to work on to produce secure by design computing system. Now these are different research aspects. I hope I was able to summarize. I'm working on them, and these are some topics on my future research. Now let's talk about the take-home message from this presentation. So let's talk about the conclusions. So what I understood in my last 4 to 5 years understanding of security, that security has become the first class design constraint, and computing must be seen beyond classic. Gone are those days when performance was the only parameter to be judged. Now security must be given its prior importance. It should be a primary design consideration into our future systems. Modern security challenges are emerging from the way we are computing today. The software execution on the hardware is doing these attacks. So there are radical changes at both hardware level and the software level to cope up this challenge of today and even tomorrow, and to make systems more sustainable. And then no computing platform is secure today. Either we are talking about the security intended efforts or ARM Trust Zone, Intel SGX, we are doing isolations very perfectly, but the attack surface is still there, still attacking those, and it is going to even expand further. So there are tools which are required to contain these existing vulnerabilities, and the future systems should be made more predictable. So this is all about the conclusions. And these are some relevant publications if someone is interested to see more about my work, because I have been presenting some of the results, encouraging results. If someone is interested, he or she can go to these conference papers and journal papers to look more into them. And here I would like to thank you to listen to me. And now I'm more open toward discussions and questions if you have any.